All right, let's talk about the secret sauce that makes the AI you use every day feel so fast and, well, affordable. It's this hidden engine humming away in the background, a piece of tech called KV caching, and it's one of the most important parts of the whole system.
Yeah, this quote really nails it. At the end of the day, it all comes down to one number, the KV cache hit rate. Get that number high, and you unlock massive performance. But as we're about to see, this isn't just some simple efficiency trick. It's a true double-edged sword, and it introduces some fascinating and, frankly, pretty scary new problems.
And look at this. The money side of things is just wow. We're not talking about shaving off a few pennies here. Some of the major providers literally have a 10 times price difference. If your request hits the cache, it's 10 times cheaper. So a high hit rate doesn't just make your app feel snappier, it completely changes the economics of whether you can even afford to run it. And then there's the speed. 57 times faster. I mean, just let that sink in for a second. We're talking about a system with smart, cache-aware scheduling delivering the first word of a response 57 times faster. That's the difference between an AI that feels like magic and one that just feels slow.
So, here's the big question for our explainer today. We've got this incredible tool that gives us huge wins in cost and speed. But what happens when that exact same tool, the one designed to make everything better, opens up a whole new can of worms?
Okay, so to really get what's going on here, we've got to start with the basics. What even is a KV cache? The simplest way to think about it is as the AI's short-term memory. So, you know when you type a prompt into an LLM? For every single word or token, it has to do a ton of math to figure out what it means in context. These calculations are called key and value tensors. The KV cache is just a spot in the computer's memory where the model saves those results. It's kind of like a chef who pre-chops all their onions and carrots in the morning. Instead of starting from scratch for every dish, they can just grab what's already prepped. It saves a massive amount of work.
So how do the big companies, the LLM providers, actually use this to make things cheaper and faster for you and me? Well, it all comes down to a really simple but powerful idea, the shared prompt prefix.
Okay, look at these two prompts. See how they start exactly the same? Imagine you are an IT expert, and so on. The only difference is that last word. The system is smart enough to see that shared part and say, hey, I've already done all the hard work for these first 11 words. So for that second request, it just reuses the work from the first one and only does the new calculation for the word Linux. That's it. That's where all the savings come from.
And, this isn't some niche, experimental thing. We're talking about the big players. OpenAI, Google, DeepSeek, they're all doing this in some form. Sure, they've got slightly different rules about how long your prompt needs to be or how they charge you for it, but the basic idea is exactly the same. Never compute the same thing twice.
Okay, so far, this sounds amazing, right? A total win-win. But that's when you're just thinking about one computer. What happens in the real world when you're trying to serve thousands of people at once across a massive fleet of servers? Well, that's when we hit our first major snag.
It's a classic problem called cache thrashing, and it's a total nightmare. Imagine you're having a conversation with an AI. Your first message goes to server 1. Great, it does the work and caches your conversation so far. But then your next message comes in, and the load balancer, which has no idea about the cache, just randomly sends it over to server 2. Well, server 2 knows nothing about what happened on server 1. So it's a cache miss. It has to redo all the work from scratch. Suddenly, all those amazing benefits of caching are just gone. So, how do you fix this mess? Well, engineers came up with a really brilliant solution. Instead of using a dumb load balancer that just throws requests around randomly, they built a smart scheduler, one that actually knows where all the caches are.
It's actually super clever. Think of it like this. Every single server in the network is constantly shouting out updates. Hey, I just cached this prompt. Or, whoops, I just had to delete this one. A central service is listening to all this chatter and using it to build a live global map of where every single piece of cache data is. So now when your request comes in, the scheduler isn't blind anymore. It just looks at its map and says, aha, the cache for this conversation is on server 3 and sends you right there. Problem solved.
So, problem identified, elegant solution engineered. Case closed, right? Everyone can go home. Well, not so fast. This is where our story takes a really dark, unexpected turn.
A research paper comes out and it drops a bombshell.
It turns out that this super smart scheduling solution we just talked about, the very thing that was supposed to fix everything, it accidentally created a brand new and pretty dangerous security hole.
The name of the attack is PromptPeek, and it's what's called a side-channel attack. That means the attacker isn't hacking the code or breaking encryption. No, they're just watching. They're watching for tiny clues the system gives off as it just goes about its normal business. It's like cracking a safe not by picking the lock, but by listening to the faint clicks of the tumblers. And what they figured out is that an attacker can tell if their prompt starts the same way as someone else's just by watching how the server responds.
So here's how it works, and it's kind of terrifyingly simple. The attacker basically spams the server with a ton of their own requests, and hidden inside that flood of traffic are their guesses about what someone else, the victim, is typing. Now, if one of their guesses is wrong, nothing happens. But if they guess right, bam! That one request gets a cache hit, and the smart scheduler sees it and says, "Oh, this one will be easy," and it bumps it to the front of the line. The attacker sees their request jump the queue, and they know they've guessed a word correctly. Then they just do it again and again, word by word, until they've rebuilt the entire private prompt.
And get this is not some academic what-if scenario. It actually works, like really well. The researchers achieved a 95% success rate in rebuilding prompts, even when they had no idea what the prompt was about to begin with. That's basically perfect. We're talking about anything from your private medical questions to a company's confidential strategy documents, just leaked.
So now we're stuck. We're facing this classic and really difficult engineering trade-off. It's a dilemma that gets right to the heart of the AI systems that we're all starting to rely on every single day.
The researchers themselves put it perfectly. The very features we build to make AI scalable and affordable, like sharing a KV cache, are the exact same features that can open up these totally new and unexpected ways to attack the system. By optimizing for performance, we accidentally created a vulnerability in security.
And at the end of the day, there are no easy answers here. We could turn off these smart features, but then AI becomes painfully slow and maybe too expensive for many people. Or we leave them on and accept this risk. It leaves us and the entire industry with a really tough question. What do we choose? Blazing speed or rock-solid privacy? Because right now, it kind of seems like we can't have both. Thanks for watching.